In this video, we will develop the differential equation that relates the internal moment in a beam to its displacement and slope. This particular equation forms the basis of various methods that are used to compute deflections in beams. So let's consider a beam with some arbitrary loading. So this is our beam. It has some arbitrary distributed load. And we're focused on the case where the beam is initially straight and it's loaded perpendicular to its local x-axis. So remember, the local x-axis is always along the length of the member. So again, this beam has a arbitrary distributed load. It also has a point load. We'll define the displacement in the perpendicular direction as B. And then what we're going to do is we know that this loading is going to cause some internal deformation, right? So we can look at the deflected shape, and this is going to cause some internal deformations as well as shear forces and bending moments. However, if the length of the beam is much greater than the cross-sectional dimensions, then most of the deformation is actually going to come from bending. And this is the case that we'll consider, right? So we're only considering the deformations that are due to bending. We're also just going to focus on an infinitesimal length of the beam that we will call dx. And we will say that the starting point of that segment is at a distance x from the left support. We can also try to visualize the slope associated with that segment dx, right, where the slope is based on the tangent at the start of that segment, and we'll call that slope, we'll call that theta. Now let's look at this particular segment both before and after deformation. So we'll draw the before case on the left. So again, the length of the segment is the x. We'll assume that the moments are positive. We're also going to draw the location of the neutral axis. And let's consider let's also consider a part of the cross section that's located at a distance y from the neutral axis. And we'll call this particular part, we'll call that ds. Now let's look at the case after deformation occurs. So we'll start with the undeformed, and so after deformation occurs, you're going to have something that looks like this. Now, we're making the assumption here that plane sections remain plane. And after the segment has been deformed by the internal bending moment M, the angle between those two cross sections, which were originally parallel to each other, the angle between them, we'll now call this d theta. Now, if we look at ds, or if we look at the location where we defined ds, which is a distance y from the neutral axis, the length of that arc, let's call it, has actually changed. So we'll call this ds prime. And because dx is located at the neutral axis, the length dx actually does not change. Right, so at the neutral axis, that distance remains as dx. So we'll say before deformation, after deformation. Now, we should keep in mind that any arc that's not at the neutral axis, the length, it's going to be subjected to axial strain, right? So the length of that arc is going to change, right? So in this case, we're focused on ds, but any arc that's, again, not aligned with the neutral axis is going to be subjected to some strain. We're also going to define a radius of curvature of the arc dx, right? And that radius of curvature will denote as rho. Right, so again, that radius is measured from the center of rotation of the two planes to the arc dx. Now, the next step would be to compute the strain in the arc ds. So let's do that. So we want to compute the strain in the arc ds, and that would just be given by the change in length, which is given by ds prime minus ds over the original length. We also know that from the undeformed shape of the segment, we know that ds and dx are the same. And we also know that we can approximate for small angles, we can approximate dx as the radius of curvature times d theta. All right, so if we go back, d theta is the angle between the two ends, the planes that define the two ends of the segment that were parallel to each other before deformation. Okay, so the length of that segment after the section has deformed is going to be ds minus y times d theta, right? So the change in length is given by y times d theta. But we've said that ds is also equal to rho times d theta. So we can write ds prime as rho minus y d theta. So now if we substitute this expression for, if we substitute expressions for ds prime and ds into the equation for strain, we get that the strain is equal to rho minus y d theta minus rho d theta divided by rho d theta. Right, so we're basically substituting these equations into the strain equation above. And then we can divide things. If we divide things throughout, the d thetas cancel. We end up with an expression that says the strain is equal to minus y over rho. Or another way of writing that is 1 over the radius of curvature is equal to minus the strain over y. Okay, so we have this expression that relates the radius of curvature to the strain in the segment ds and the distance of that segment to the neutral axis. Now we're going to introduce Hooke's law, and we're also going to introduce the relationship between the bending moment and the axial stress. So we know from Hooke's law that the strain is just equal to the stress divided by the elastic modulus. We also know that the stress is equal to minus my over I, where I is the moment of inertia, y is the distance from the neutral axis, and m is the bending moment of the segment. And then earlier, we also established a relationship that 1 over the radius of the curvature is equal to minus the strain over y. So if we put all of these three equations together, we end up with 1 over the radius of curvature is equal to m over ei. Again, E is the elastic modulus, I is the moment of inertia. Now, recall that we established that dx is equal to rho d theta. So if we substitute that into this equation, then we get d theta dx is equal to m over ei. right? Where d theta dx is the curvature. Another way we can write that expression is that d theta is equal to m over ei dx. Now, from calculus, we know that the curvature can be expressed in terms of the displacement in the local y direction, right? So we know that the curvature, or 1 over the radius of curvature, is given by this expression. And again, that's from, this is from basic calculus. So if we replace 1 over the radius of curvature with m over ei, we end up with this expression. And assuming that the rotations are small, so we're assuming that dv dx is close to 0, that means that we can approximate 1 plus dv dx squared to the 3 over 2. We approximate that as being equal to 1, because for a small dv dx, this expression goes to 0. And so what we end up with is that the second derivative of the displacement with respect to x is equal to m over ei. And we know that this second derivative is the same as the curvature. So this is the differential equation that relates the internal moment in a beam to its displacement and slope. Right, so we know that, and by that we mean that B is the displacement and dv dx is the slope.